Hi everyone, welcome to another LIC class. Uh, Before we start, I'm going to do a quick written quiz, and then today we will continue with the feedback systems. We did series, parallel, and parallel series. We finished. Today we're going to continue and finish the parallel, and series op-amp systems. So let's start with this quick quiz. So imagine we have an op-amp and the positive or the non-inverting input is connected to a DC power supply. And this is 1 volts. This would be 30 ohms. And this one would be 6 ohms. And it is connected to another DC power supply. And this one is 3 volts. We want to find the output voltage. And imagine that this is the ideal op-amp. By the way, I had some questions about the homework. Any of you, did you solve the second homework? No? So second homework, third question, parts B and C, those are summing and difference amplifiers. And I've already solved a couple of practice problems for summing and difference amplifiers. So you just have to use those equations and just put in the values and calculate the output. Okay. I'll give you a few minutes to think on this. By the way, this is not a non-inverting amplifier because the negative input is also connected to an input signal. So the best way to solve this, there are a couple of different ways to solve it, but the best way is to use the principles of an ideal op-amp. V positive is equal to V negative, input current is equal to 0. And you can use KVL, KCL, Kirchhoff's current law to be able to solve this. Do you need more time? Or do you want me to give you a hint? Okay. So the voltage at this point, this is V positive, okay? And I'm gonna call the voltage at this node VA. And since V positive is equal to negative, then VA is equal to V positive, which is equal to how much? 1 volts. Yes. So now you know the voltage here, okay? So we have two currents coming. This is, I'm going to call I1, I2, and this is IN. And what is an input current for an audio op amp? 0, perfect. So therefore, I1 plus I2 using Kirchhoff's current law is IN, or I1 plus I2 is equal to 0. Now, what is I1 equal to? It's going to be its voltage, the voltage of this resistance. I'm going to VR1 over R. So I1, according to Ohm's law, it's VR1 over R1, and I2 is VR2 over R2. Now, what is VR1? It's going to be 3 minus VA over its R. What is VR2? It's the output voltage, V out minus VA over R2. Okay. We're taking a quiz. You can pick a paper and write the question. Ian, just participating, you get some credit on the quiz. Yes. Writing down the question, if you don't have time to finish it, you don't get once. So again, you can use the principles of an ideal op amp, that V positive is equal to V negative. Input current is 0. So therefore, I1 plus I2 would be equal to 0. And using the Kirchhoff's current law, you can find V out. Okay. I think that's had enough time. So let's start with the course. Today we're gonna continue the feedbacks. We're gonna specifically speak about parallel and series feedbacks. So just a quick review. Feedbacks has multiple benefits in the system. First benefit that we get from a feedback is to give control over the output. And by having a negative feedback, we can control the gain. And by controlling the gain, we can control the output. And that is necessary for different amplifiers. So for example, if you have an audio amplifier, you want to have control on the volume, on the output gain, and the amplitude of the voltage. So you needed negative feedback. But there are some trade-offs with feedbacks as well. When you have a negative feedback, you would decrease the gain. So for an ideal op amp, without any feedback, the gain would be infinite. So open loop gain is infinite. So I'm gonna mention open loop is infinite for an ideal op amp. But when we add a negative feedback to it, we reduce that gain. But on the other hand, what we do is we increase the bandwidth. So by adding the feedback, we increase the frequency response. Therefore, the system works in different frequencies. But for an open loop system, the gain is high, but the feedback, the frequency response is very limited. Therefore, you're going to filter a lot of frequencies. We spoke about different configurations of feedback, such as voltage series, current series, voltage shunt, and shunt, or in other words, series parallel, parallel series, and parallel systems. And these different systems work well with different applications. So if you need a voltage amplifier, if you can use a voltage series, for example, op amp. If you need a current amplifier, you can use a current series, and so on. Yeah, we went through different feedback configurations, how they are connected. So for example, a parallel, you have a parallel connection in the output, which is getting a sample from the voltage and feeding back that as a current to the system. And series, you're getting the current example or a sample from the current, and you are feeding that current as a voltage back to the system. So when you have anything connected in the output of the system as series, you're going to get the current. It's like a ammeter, and when you connect it in series to the input, you're giving it back as a voltage sample, like when you connect two batteries in series, I can say. And we reach up to this point. So series parallel connections. Series parallel connections are ideal voltage amplifiers. We use them especially in audio amplifiers. It has a series input because there's no input current node. So you can see that in a series parallel, we're getting a sample from the voltage and giving current and feeding it back as the voltage to the system. And we had the example here, I think here, yes, the series parallel connection. So you can see that we're getting an example from, for example, this one. We're getting the voltage because it's connected in parallel. So we're getting a voltage example or a voltage measurement, and then we are feeding it back in series. Therefore, we are providing voltage to the system. And this is a block for a series parallel, or what we called a voltage series. They also call this a voltage series system as well. So voltage meaning you're going to get the voltage in the output, and you're going to get this in the output. And in this system, you have the series and parallel. So in the feedback, you have voltage series, and this main system is connected in series and parallel. This is an example of a series parallel system. Let's say that the microphone that you use for acoustic instrument produce a signal that is just too weak for you to record without excessive noise. After a little experimentation in lab, you discover that you need about 20 dB of voltage gain before you can successfully capture and softly pick your guitar. Using this figure, this is actually a book example. The open loop gain is 50,000. The input impedance is 600 kilo ohms. So my question is this. First, what type of amplifier is this? Is it an inverting or a non-inverting amplifier? Inverting. So where is the input connected to? Is it connected to the non-inverting or the inverting? Non-inverting. So this is a non-inverting amplifier. Okay. So what is the gain for a non-inverting amplifier? Is 1 plus RF over R1. Am I correct? Or RI. So if you want a gain of 20 dB, first we convert that 20 dB to the gain. That gives us a gain of 10. So we simply replace 10 is equal to 1 plus RF over RI. In other words, 9 is equal to RF over RI. So the ratio between RF and RI should be 9. So RF could be 90 and RI could be 10, or it could be 9 and 1. Any ratio would work, okay? But the gain should be equal to 9. So RF should be 9 times as RI. The parallel series connection is the opposite of the series parallel form. The negative feedback is again used to make the ideal current amplifier. So series parallel is a great voltage amplifier. Parallel series is a great current amplifier. Okay, so keep this in mind. This is a very good current amplifier, and the previous one is a great voltage amplifier. So if you have a question in your first exam, for example, asking which of the following feedback system gives us the best voltage amplifier, it's gonna be series parallel, and parallel series gives us the best current amplifier. It produces a low input impedance and a high output impedance. So it's ideal for a current source. The signal source's current splits into two, and with parts going into the amplifier and parts going in through the feedback network. This is how we know that it's a parallel series connections. So as you can see, you get a sample from the output current, and it's connected in series, and it's again connected to the input voltage. And this is a configuration for the system. So this is a great current amplifier. If you want to create a current source that has, for example, a 6 amp fixed output current, this is a great way to do that. So the next type of feedbacks are the parallel, and the series connections. Parallel, and series connections are not used as amplifiers at all. They are usually used as transducers. So voltage to current and current to voltage transducers are made using parallel, and series connections. Again, they usually don't produce any gain. Maximum gain is maybe 1. They are neither voltage amplifiers nor current amplifiers. Instead, they are used as a transducer, like a voltage to current and a current to voltage. So transducer mainly means a device that converts one form of energy to another. So these, and I'll explain that in the next slides, and then next chapter, we're going to start with the transducers. So we have voltage to current and current to voltage transducers in this class. So we convert voltage to current or current to voltage. This is a parallel configuration, and this is a series configuration. So this is a voltage to current transducer, and this is a current to voltage transducer. Do you have any questions up to this point? Okay, no. So just a quick review, and we're gonna have the second question on the quiz. So we had the different type of configurations for amplifiers. We had the non-inverting and inverting amplifiers. All of these configurations have a feedback in them. You can see that here RF is our feedback system. This is a passive feedback. The feedback gives us control over the output voltage, and we would also increase the frequency response in the system. So in this system, we have a very high input impedance, very low output impedance, and obviously adding the feedback reduces the voltage gain. The equation for non-inverting amplifier Vout was 1 plus R2 over R1. And for a non-inverting amplifier, and we also had the second one was the inverting amplifier. And for an inverting amplifier, the output was negative R2 over R1 Vn. And the same thing we had, we have a feedback in the system which reduces the gain, but increases the frequency response. This is just a quick reminder of differential amplifiers. And this is very similar to the question that you had on your homework. I had some questions about this. So summing and differential amplifiers, you can use the equation that we had. You simply have to replace R1, R2 to be able to solve these. We had voltage followers, which is a voltage buffer. The gain is equal to 1. And finally, we had the voltage competitors. So a voltage competitor doesn't have any feedback. Voltage follower has a feedback of 1, just connects it. So technically, the feedback, you can see it's actually 0. So the gain is one and it's a voltage follower system. It's a buffer. And as we can see, differential amplifier has the feedback and negative feedback. Also, the inverting amplifier also has a feedback. So anything that you see that has a connection between its input and output would be a feedback. And since the voltage competitor doesn't have any feedback, the gain is technically infinite. But since we have limitations, the upper and the lower output is limited to the power supply input, the positive and negative power supply terminals. So it will be saturated as positive VCC or positive power supply and negative VCC. So this is very good for creating a clock system, a pulsating, I can say square signal, which is used a lot in digital systems and power electronics. Now, the second quiz question. We have a current source connected in parallel with a resistor. Just give me a second. Negative, this is positive, this is connected to the ground. This R1 is, and this is Rn. This is 1 milliamps. Rn is 5 ohms. R1 is 2K, and R2 is, or let's say this is 2 ohms, and this is 42 ohms. So 2, 42, and 5. And we want to calculate V out. I'll give you a few minutes to think. You want me to give you a quick hint? Yes. So easiest way to do this is you can use these two elements and convert a current source to a voltage source. So if you have a current source which is in parallel with the resistance, and this is IS and this is R, you can convert it to a voltage source which is connected in series with the same R. And this voltage source now, the new voltage source would be ISR. Now you have a voltage source connected to a resistor. And the rest is pretty easy and straightforward. So for example, here, if R is 5 and this I is 1 milliamp, V would be 5 times 1 milliamp. It's going to give you 5 millivolts. And this would remain 5 ohms. But now there's 5 ohms, so we can replace it, the whole system, with this. You have a 5 volt connected to a 5 ohms, connected to another 2 ohms, connected to the 42, and the op amp, and the output. So 42, 2, 5, 5. Now these two would be in series, so come on. Okay. That's it for today. I just wanted to also take this time to ask about your first midterm. Your first midterm would be around the 3rd week of October. I want to know when is the best time for you. I know you have other exams. So I was thinking on 22nd maybe, or 15 or 22nd. One of these would be good. So again, it's up to you. I have a conference I think I have to attend by 25th. So it's better to take it on 15 or 22nd, or even 29th would be okay with me. So please let me know what's the best time for you, and check your calendar and see if you don't have any exam on the same day, we can schedule for one of these, like 15 or 22nd or 29th, right? At the same time as the class. Okay, or let's say 17th. I think 17th is better. 17th, 22nd, and 29th. Okay, thank you so much, and I will see you on Thursday.